it's a turn of an innovative project aimed at detecting air quality stations with anomalies and inconsistent outputs using a machine learning approach. They have used the principal component analyzed K nearest neighbors and copula-based outlier detection methods. The teams behind this project is Mohit Anand and Kumar Shridhar. It's a pre-recorded presentation. The floor is yours. I hand over to you.
Good afternoon, everyone. I'm Mohit and I'll be presenting the work I did with Kumar Shridhar on detecting anomaly in air quality stations as a part of ESoC 2020 project. Our supervisors were Johannes and Miha. Without any further delay, I'll quickly delve into the current situation. Copernicus Atmosphere Monitoring Services releases gridded 3-hourly average global air quality data. OpenAQ, on the other hand, is a non-profit organization that collects point measurements from the stations around the globe, but no quality control and station classification is applied to the data. So OpenAQ stations needs to be analyzed before being used directly within or alongside CAMS data. Our objective was to identify all such OpenAQ stations which are not representative for a particular location, and if we wanted to use machine learning and AI to find anomalies in the observed data. We also wanted to use spatial and temporal information that is embedded in the data for making a well-informed classification. And at the end, we always consulted with the experts to validate our hypothesis. The idea was very simple, and it was to compare each OpenAQ stations with nearby OpenAQ stations and with nearby CAMS reanalysis data. But there were 3 major challenges in this. First and foremost, what is nearby? Second, how to compare gridded data with point data? And third, how to compare irregular, inconsistent, and long time series. Talking about these challenges, for finding out what was nearby, we divided the entire world based on CAMS grid, which is a 0.75 degrees cross 0.75 degrees. And for each grid, the nearby 8 grids surrounding it was classified as nearby locations. For comparing gridded and point data, we assumed CAMS data coming from the stations which are located at the center of each grid. And then the third point was about inconsistent and irregular long time series. So we had 1 year of OpenAQ data and 1 year of CAMS data. So we divided the entire data into 7-day period comprising of 52 different weeks. We averaged the data based on the time of the day. So we created 8 bins of 3 hours each. To explain it better, what you see on the right is a typical plot where we first select a day, which is here 25th of October 2019. We then select a span. Span is simply the number of days before and after this date for which we are considering the data. So span of 3 clearly indicates that the total number of days considered here was 7, including this day. Then we select a parameter here, PM 2.5, and we find out what was the average concentration for 7 days between 0 to 3 am, 3 to 6 am, going so forth and so on. What was the average PM 2.5 concentration for 7 days between 21 to 24 hours? Then we apply some machine learning outlier detection algorithms, namely COPOD, which is a copula-based outlier detection method, KNN or K nearest neighbor, and then PCA or principal component analysis based outlier detection method. Using these 3 methods, we classified stations as dissimilar type A or similar type B stations. But this was done for data for each week, and we had to find a way to combine our data for 52 different weeks. We used a threshold-based method where if for more than 90% of the weeks, here 52 in total, a station was classified as dissimilar or type A, then that station was classified as type A or dissimilar for the entire period of time. I'll quickly go into some of the results that we have. Here we are comparing OpenAQ versus OpenAQ for 3 different machine learning types: COPOD, KNN, and PCA. And the species we are using is NO2, and this is expressed in parts per million, and this is the hour of the day. What we do see here is red and blue are OpenAQ station data, and yellow is the CAMS data really at the bottom. But here we are just making OpenAQ versus OpenAQ classifications. So based on that, our method did find this data coming from this particular station as type A station. So obvious outliers are easily classified as type A in all the three different methods, but not so obvious one like this blue line is classified as an outlier in KNN, but not an outlier in COPOD and PCA. And some of the results varied here as well. And this was for a reason around Delhi. I'll show you one another plot. This is OpenAQ versus CAMS data comparison for three different machine learning types for a region around Delhi for PM 2.5. And what we first see is that CAMS data is in yellow. So CAMS data very well agrees with the OpenAQ data in their spread and as well as the diurnal cycle. And what we also see that some of the methods here, COPOD and PCA, are able to find out easily observable outliers, while KNN was not able to classify the data coming from these stations as an outlier. Then moving on, for some cases where there was a strong biases in the data, and here we are making OpenAQ versus CAMS classification. Like all the red ones are the OpenAQ data and the yellow ones are the CAMS data, and the species here is NO2 and it's also expressed in ppm. What we do find that for all different methods, all the OpenAQ stations are classified as type A stations because of the strong bias in the data coming from CAMS data. But we move on to some interesting result with PM 2.5, and here we do see is in the yellow are all the data coming from CAMS, in the red and blue are the data coming again from OpenAQ, and this one, the data coming from this particular station is not classified as an type A in first two methods like COPOD and KNN, but in the third method PCA, all the three data coming from OpenAQ stations are classified as type A. Then when you summarize this over entire time period for 52 weeks, we can make a regional map. Here we are considering the Europe region, and this is OpenAQ versus OpenAQ and OpenAQ versus CAMS. The parameter used again is PM 2.5 and the method used is COPOD. What we see is of the total 755 stations, type A stations were only 29 when we compare OpenAQ versus OpenAQ, but they went up to 382 when we were comparing OpenAQ versus CAMS data. And when we do the same thing for Europe region, considering ozone, we have similar results, like type A stations were very less for OpenAQ versus OpenAQ, but for OpenAQ versus CAMS, the type A stations increased dramatically. What we also see here, and as well as in the last plot, we see a strong clustering, like most of the OpenAQ stations which were classified as type A stations belong to a particular region. This could be indicative of the fact like the data coming from a similar network in a similar region, probably a one country or two countries, had some biases with the CAMS data, or in other way there could be even some probability that CAMS data is not predicting well for this reason. But being a model data and a continuously modeled data, this is very unlikely to see a small clusters of CAMS grid where it is not doing very well. And then we move to a different region with a different species, here sulfur dioxide. And what we do see here is of the total 206 stations, only 17 were classified as type A using OpenAQ, while when we use just CAMS data, we see 27 being classified as a type A stations. And we also do this for ozone, and here only 17 were classified as type A out of 205, while going to the comparing it with CAMS data, we see a lot more, like 64 stations were classified as type A compared to the total of 209 stations. So finally, summarizing the entire results, we can get this global plots. Here we are using parameter as PM2.5 and we are comparing OpenAQ with CAMS, and we find like of the total 3,643 stations, 717 stations were classified as type A. But what we also see that there are major clustering, like most of the type A stations are in one part of Europe, some part of USA, and then again some part of China. This could, as I talked earlier, this could be indicative of some regional network biases data coming from OpenAQ. To put the statistics and the numbers, and this is for OpenAQ versus OpenAQ, we had total 3,600 stations for PM2.5, 3,900 roughly for NO2, 4,300 for O3, and 2,800 for SO2. These are number of type A stations using different methods, COPOD, KNN, and P. P stands for PCA. For COPOD, we could really see like number of types A stations were really high compared to the other two methods for when comparing OpenAQ versus OpenAQ. This is really indicative of the fact like OpenAQ data, that COPOD is a very stringent method to find type A stations for when comparing OpenAQ versus OpenAQ. But what we also see, like there is major overlap between the different methods. Like of the total different 52 type A stations from KNN and 51 type stations from PCA, 36 were commonly identified as type A stations using K and T. So we see that there is a very strong agreement between the different methods, while COPOD being this most stringent one. And just to give us some information about the tools and the codes that we created an open source machine learning tool repository called as DAAQS, and it is available to see and work with or play with. The documentation is also available on this link. And what we see on the right is a small snippet code. You just need to choose a location, give it some name, find the latitude and longitude of that particular location, choose a day, as I explained, choose a span parameter and what you want to compare with, whether it's OpenAQ versus OpenAQ or OpenAQ versus CAMS. Choose the method, and then with the next 10 line of code, you can get very expressive plots. One of the major thing of our repository was it could get good plots and even statistics. Just to summarize, we created an open source machine learning tool to classify similar and dissimilar weather stations. COPOD detected the largest number of dissimilar stations and is the most stringent one, especially when comparing OpenAQ versus OpenAQ. But this is not the same when we compare OpenAQ with CAMS, where all the three different methods do equally, like perform reasonably stringently, like they have same number of type A stations. Comparing OpenAQ stations with CAMS data was difficult, especially if CAMS data had large biases, but this is the only method available if we have very less number of OpenAQ stations in the vicinity, because then no statistical method could be applied for OpenAQ versus OpenAQ. And OpenAQ versus CAMS comparison also helped us in detecting regional biases that could be coming from network that is available into a particular region. That is what we saw in parts of Europe and US. And that is all from our side, and we are open to questions. So thank you.
Thank you very much, Mohit, for your presentation.
Yeah.
Really outstanding your work. We have a comment question.
Yeah.
I would like to read it for you. Perhaps in a slide, you can go to the slide, but I repeat again. Perhaps it could be interesting to also sub-classify the type of outlier.
Yes, exactly. Yeah, that's a good idea. And we were just started with this and we did some type of classification. And it was mostly the challenge was with a large number of data for many different, different locations. So we wanted to keep a method which could just tell us what are like dissimilar stations. Yes, a further work for sure would be to subclassify it, like why a particular type of station is being classified as type A or dissimilar station. Yeah, I agree with that.
Thank you. Another question for you. 7 days, an average of each hour. How do you account for the weekend holiday effect?
Okay. Yes. Right now, the thing is, we are not accounting for any holidays or weekend, like the biases that might be coming due to the weekends. But in our understanding, we did not need to do that because we were only comparing OpenAQ data with the other OpenAQ stations nearby or the CAMS grid data nearby. So if there was a weekend in a particular, like when we take 7-day averages, like that thing is entirely average for each of the case. Yeah, like that is what our understanding was, because it didn't change the, like it was not that we were comparing weekend data with non-weekend data, we just averaged for the same time duration. So in a way that effect should be taken care of. That is what our understanding is.
Thank you very much. No
Yeah.
questions so far. Thank you, Mohit.